In section 2.4, we look at a library of functions. So these are functions that you will commonly come across when you're graphing different functions in this class. So the first family of functions that we'll consider are the power functions. That look like y equals x to the n, where n is a natural number. Whenever you hear natural number, that's just the set of numbers 1, 2, 3, 4, 5 onward. So if you're looking at y equals x to the first power, that's the easiest graph you can possibly graph. That's just a straight line cutting through the origin. Y equals x squared is just as easy, a parabola. Now, before we proceed with other variations, consider some of the characteristics of these two functions. For x to the first power, on the far left-hand side, as your x's go to negative infinity, your y's go to negative infinity. On the right-hand side, as x goes to positive infinity, your y values go to positive infinity. For y equals x squared, as your x's go to negative infinity, far to the left-hand side, your y values go up to positive infinity. And on the right-hand side, as your x's go to positive infinity, your y values go to positive infinity. Knowing the characteristics for these two gives us a lot of leverage for any other function of this format. If you were to graph out y equals x cubed, that's a cubic function. Oh, don't want to erase that. And notice that the end behavior of this function is very similar to the end behavior of x to the first power. If you were to graph out y equals x to the fourth, it just the base model x to the fourth looks very similar to parabola. So the end behavior of x to the fourth is very similar to the end behavior of x squared. And that will always happen when you're considering these types of power functions. So if you have a power function in front of you later on, like maybe something more complex, like y equals, let's say 7x to the fifth minus 3x squared plus x minus 12, before you sort of run through your calculator and try to graph this whole thing, you have a lot of insight on what's going on the far left and on the far right just by noting that this guy has an x to the fifth in it as its highest power. So since this is x to the fifth, that power is odd, so I know that it's going to have the end characteristics of these odd power functions. So I know that for this graph, on the far left-hand side, this graph is going to go down to negative infinity, and on the far right-hand side, this graph is going to go up to positive infinity in the same way that x to the first power and x to the third power had those characteristics. Now, for the stuff that happens in between, that's a different story. You would have to do some analysis, and then later on you would have to use some calculus to fill in the gaps of what happens in between. But knowing what happens on the far ends, the end behavior, is really powerful to get some clarity about where the graph is coming from and where it's going to. Another type of common family of functions are the rational functions of the form y equals 1 over x to the n, where n is a natural number. Again, 1, 2, 3, 4, 5, etc., etc. We can get an insight on the family of these functions by doing them one at a time. So if you were to graph out 1 over x, we saw this one earlier in class. This guy looks like that. And just for reference, I call these guys the flip functions because when x equals to 0, on the left-hand side, the function goes to negative infinity, and on the right-hand side, it goes to positive infinity. So it flips from negative infinity to positive infinity as you cross 0. Notice that for this function, on the far left-hand side, the y values go to 0. On the far right-hand side, the y values go to 0. And right in the middle, again, you have that flip. Let's compare it to our function 1 over x squared. On the left-hand side, the graph of this looks like that. And on the right-hand side, it looks like this. Notice that in the middle, you don't have that flip. From the left-hand side, you're going to infinity. From the right-hand side, you're going to infinity. For reference in class, I'll be calling these guys a volcano. It sounds kind of silly, but you'll remember it forever. So 1 over x squared are the volcanoes. So again, for these 1 over x squared functions, on the left-hand side, the function goes to 0. On the right-hand side, the function goes to 0. And right in the middle, you don't have that flip. The function is going to the same infinity on both ends. And these are the two functions you want to have in mind whenever you're working with rational functions, because if any other rational function of this format comes your way, you can compare them to either one of these two functions. So in this case, because I have 1 over x cubed and 3 is odd, I'll compare it to this 1 over x to the first power, and I'll know that this function will look like this. So 1 over x cubed has that flipping characteristic where it goes down to negative infinity on one side and positive infinity on the other. And if you had y equals 1 over x to the fourth, I would compare that to 1 over x squared, and then the graph will look somewhat like this. So of course, if you were, let's say, taking a test or doing some homework, you could always run and get your calculator and type this in, but just knowing these templates for 1 over x and 1 over x squared allows you to deal with this process a whole lot quicker. Now let's take a look at root functions. For root functions, you can think of them as the nth root of x, or y equals x to the 1 over n power. These two are exactly the same. For the first function that we'll consider, let's take a look at x to the 1/2 power. What's x to the 1/2 power also known as? That might be more familiar to you. X to the 1/2 power is the same thing as the square root of x. So this guy, we know to have this graph. Notice that this function only has x values in its domain from 0 to infinity, because you can't plug in negative numbers into a square root. Compare that to x to the 1/3 power. also known as the cube root of x. Before we graph this, can we plug in negative numbers into these x's? You definitely can, because if we put a negative number here, you could take the cube root of a negative number. So this guy has a domain from negative infinity to positive infinity. And if you were to graph out the graph, it looks something like this. One thing to note about these root functions is their end behavior. For the square root of x, these y values go to infinity. You might say, well, yeah, of course. But if you were to graph it on your graphing calculator, you would see that these go to infinity, but really slowly, to the point where it almost seems like they're leveling off. So that could mislead you. So just be aware of that. These root functions go to infinity. And same goes for this guy. On the far left-hand side, this guy goes to negative infinity. On the far right-hand side, this guy goes to positive infinity. But if you were to graph it, it looks like the y values level out. And they don't level out. They go to infinity, but they go to those infinities really slowly. So something to be aware of. Now we're going to consider the absolute value function. Y equals absolute value of x. I'm sure you guys are familiar with this. Whenever I graph an absolute value function, I think about a v with the point 0, 0 right in the middle. When considering an absolute value function, sometimes it's convenient to decouple this graph into two pieces. First of all, if we were just looking at the right-hand side and completely forgetting about the left-hand side, what function is being represented on the right-hand side? Is that a function that's familiar to you? That's just y equals x. So this guy right here is y equals x. And that guy right there is y equals negative x. So whenever you're thinking about the absolute value function, you can actually write it as a piecewise defined function, telling the reader, hey, within this section of x's, the value of the function takes on this form, and within this other section of x's, the function takes on this other form. So for x values that are negative, the values on the left-hand side, the absolute value of x can be thought of as negative x. For values that are positive, the values on the right-hand side, the absolute value function can be thought of as positive x. And one of these has to carry the 0. Either one of them can do it. So I'm going to have this guy carry it. So when the x's are either positive or 0, you're looking at the function x. This is really important. Let me tell you that when you're doing calculus, the absolute value comes up often in different computations. And when it does, it's hard to compute things with the absolute value as is. You would often take this function and break it up using this piecewise defined structure so that you can deal with the computations easily with an x or a negative x instead of the absolute value of x. Furthermore, since we're on this topic, suppose you got a function like the absolute value of x minus 3. Suppose I cheat a little bit and I pull out my calculator and I graph this out. And when I do, I get something like this. Here we have something similar to what we had above. This graph is defined one way on the left and defined another way on the right. To figure out what the definitions are for these pieces, you kind of pull from what you saw up here with the original base model of the absolute value of x. On the left-hand side, we're taking whatever was in the absolute value and making it negative. On the right-hand side, we're taking whatever was inside the absolute value and keeping it positive. So if I'm thinking about taking the absolute value of x minus 3 and breaking it up into a piecewise defined function, on the left-hand side, I'm going to take whatever was inside my absolute value, which is x minus 3, and make it negative. So this definition is what goes in for the left-hand side. On the right-hand side, I'm taking whatever was inside the absolute value and keeping it as is. So this is what's going in for the value of the function on the right-hand side. What's the cutoff between the left-hand side and the right-hand side? Where do things change between this curve and that curve? They change at the value of 3. So this definition is true when x is less than 3. This definition is true when x is greater than 3. And I have to have one of these guys carry the 3 with it. It really doesn't matter whether you give it to the top or give it to the bottom. In this case, I'll keep it with the bottom. So whenever you have an absolute value with a little bit of shifting with it, when you have x plus or minus a number, you could always deal with that this way.